Alright, so today we will be going over transportation safety. Of course, when you think transportation, you immediately go to cars, everyone does. But there's a lot more to it, and the things that we necessarily do for the safety is not just what you'd normally expect. There's more to it than guardrails and painting lines on a road. So we're going to jump into this and have some fun. So what is engineering? Probably something you guys have probably never been asked. I know in high school I never was. To me, engineering is an unholy matrimony between science and math that causes a lot of lost sleep and deterioration of social skills. And I feel that's a pretty accurate definition. But people that have a little more experience than myself usually go a little more in depth. So, engineering rather, the application of scientific and mathematical principles to practical ends. So we take math and science and we make them useful. Probably thought math and science was pretty useful, but we do a little bit better job. At least we like to think so. Engineering, it's everything. Chemical, mechanical, industrial. Here we're focusing on civil, but there's a lot of overlap with these. Mechanical and civil are very closely related. Even chemical, whenever they design the pavement, how to stop, how your tires work on the road, falls into chemical engineering. Petroleum engineering, the products that we're making to run the cars, whether it be gas, natural gas, any type of petroleum product, diesel, as I'm sure some of you have probably used before. So what is transportation? Covered this just a little bit. Most of you probably think cars, like we said. What about sidewalks? Transportation? Yeah, you're going from part A to part B. But is it just people? And is it only when people move in big quantities? Or does it really matter? Now, what about bicycles? Will we make bike lanes on some of the roads? Maybe you've seen a few, maybe you haven't. They're there. How do we design around this? How do we get products and goods from one place to another? And what is transportation? What all does it cover? Well, safe and efficient movement of people and goods. Can't really get past that. Now, of course, it doesn't have to be safe and efficient, and it's still transportation, but safe and efficient is the way we want to go. If it's efficient, we save money, and if it's safe, well, that's a given. Nobody gets hurt. Nobody dies. Nobody wants to drive to school and think, well, the cars might fall off, or the tires might fall off the car, then we'll go off the cliff. Well, that's probably going to happen today. It happened yesterday. No, we don't want to do that. We want to try and be safe. Now, transportation engineering deals with how we do this. What vehicle do we use to transport this stuff? How do we transport it? And what do we do to make sure that it gets from point A to point B safely and efficiently? And how do we improve the safety? And how do we improve the efficiency? So what are we trying to do? Kind of already said, get from point A to B. Alright, we're trying to do that. We're trying to be safe about it. Okay, nobody wants to get hurt. Alright, we want to be efficient. You want to save as much money as possible whenever we're doing this. Efficiency and environmental concerns are kind of the same thing when you think about it. The more efficient we are at doing this, then the less materials we have to use. The more efficient a car or truck is, the less gasoline has to be in the tank. So this saves us money, and it's also good for the environment because that's less pollutants that are coming out of your car whenever you're trying to get somewhere. Now, of course, a wonderful example, in most engineering, there's no such thing as a small mistake. They always get huge. There's always a problem. And you can see here, if you make a little mistake making a bridge, things don't line up. And while that would be an awesome bridge to see, nobody wants to drive over that. If you're the person that's in charge of this entire goofy intersection, it's a pain to look at. Do you imagine designing that and making a mistake? Having one road go the wrong way into a lane? That'd be a disaster. And it would take forever to fix because once you've started building it, you're already there. So we've got to look at ways to make sure that what we're doing is safe and sound and that it's going to work. Things change. Sometimes. Sometimes they stay the same. That's a good song. I like it. Don't know who wrote it. Bummer. Anyway. Now if you're like me, you come from the middle of nowhere and there's really not a whole lot going on. There's not a whole lot of changes. Roads tend to stay the same. Areas don't really change too much. Or if you're in Morgantown, like I've been for 4 years, things have changed drastically. They've taken out intersections, put in roundabouts. There's apartment buildings that are coming up and swallowing everything around them. The university's buying half the city and putting up apartments. So things change. And Morgantown's kind of small. Bigger changes happen all over the place. And that's only 4 years. What about 5, 10, 15, 20 years in the future? We're not really sure what's going to happen, so we have to plan for all possibilities. Just a couple examples over a 30-year period of time. Humongous difference. The crowding, the number of people, the number of cars, every bit of it has gotten higher and higher and higher, and old systems just can't handle it anymore. So we need to look at ways to improve this, but also build for the future, because it's going to continue to increase and get harder and harder to maintain. Transportation engineering specialties. Just like we said, there are a lot of things that fall under transportation. Just a few examples. Bicycle, highway, port, harbor. Maybe you didn't think of ships. I know I didn't, but it's something out there. You see people on bikes, people walking, airports, how you make the pavement, how you put the sidewalks in the city, how bike lanes interact with traffic lanes, where the monorail's going, how the railroad has to go through town. Every bit of this can be a subspecialty. And there's even more for an area of emphasis. Economics, you've got to do this stuff cheaply or no one's going to do it. Psychology, sociology, maybe you've heard of road rage. Maybe just the way people act whenever there's something new. Do you take the shortcut and try to cut ahead of traffic? Or do you do what you know is going to work? Just anything that could possibly deal with what's going on. We have to make sure that somebody knows how to do it. So what transportation is not? Hopefully. Mistakes happen, we understand that. And sometimes they're just funny. Bum up. Okay, maybe an honest mistake, maybe someone can't spell. We try to avoid this. Water on a road when raining? Huh. You'd think that'd be a given, but they needed a sign. Absolutely nothing. Next 22 miles. Southern West Virginia. We need a few of those signs. Entrance only, do not enter. Personal favorite. One way. Oh, you have to go. Sorry. Don't. Drink and drive. Don't. Awesome. School tarts. Little stuff. But vastly confusing if you ever run into it, especially the one-way sign. I think I've done that before, not really sure. Alright, different transportation modes. Talked about road. Man, that gets messy. Alright, bike. Segway. Probably don't see very many people on a Segway. We have one person at the university who's been commuting on a Segway. He's ran past me a few times. But one person doesn't really mean that we have to make special infrastructure for them. Trucks, big trucks. A lot of those jackknifing on I-79 with the snow. A couple extra problems with trucks. Air transportation, the fun one. Rail, okay, that's fine. Pipes, maybe we didn't think of pipes specifically for the movement of a product, not necessarily people. Kind of the same thing with cargo ship, maritime transport. You can have people on them, but your goal isn't really to deliver people, so that's okay. It all works. So anyone have any questions so far? Alright. Transportation fun facts. I know you guys are dying to hear these. 16% of U.S. gross domestic product. So almost a fifth of all the money. Transportation. $1.5 trillion on expenditures. None of us have that much money, and it's kind of weird to think about, but yeah, you know, national deficit and kind of up on that territory. 70% of all petroleum in the United States is used for transportation. and then we use petroleum to transport petroleum. So we're just pumping more and more into the system. On average, U.S. citizens travel an hour a day. Just about anyone who rides a bus to school. I know my ride was over an hour each way. So, double that. 12,000 miles per year. 12,000 miles is a lot when you really think about it. Especially when you don't go anywhere like me, just in and around town and boom, 12,000 miles. 80% of those eligible have a license. That's a lot of people on the road to take care of. And that's 11% of the U.S. workforce. So there's a lot in transportation right now. Not so fun facts. Go over a couple of these real quick. Struck by lightning, 1 in 240,000. Better odds than the lottery. A lot better odds than the lottery. Being attacked by a shark, 1 in 11.5 million. Okay. Being attacked by a bear. Seen a couple in my day, they've never attacked. 1 in 36 million. Okay. Feeling pretty good about living a long, healthy life. Oh, wait. Being killed in a car crash over the course of your lifetime. 1 in 77. A car is going to kill you before a bear kills you, or a bee stings you to death. That's not good. It's the leading cause of death from ages 5 to 33. And 70% of children born today will be in a car crash. Now I think that's a lot, and in reality, it is a lot. So we got to try and fix this, or at least do something to help. So what all goes into transportation? First off, you have planning. Future transportation infrastructure support. Now, not only is this handling all the traffic, it's anything else you would want to put in. 50 years ago, there really weren't bike lanes anywhere. So what do you do whenever you want to put a bike lane in a city and you just have no room? It's too dangerous to put them in traffic sometimes. So if you have to go through and rebuild everything, it's a very expensive, costly procedure. We want to avoid that. And one of the things that we can use are analytics software. Maybe you've seen some of the stuff done by IBM or any type of computer programming that will actually go through and map all the routes possible for every car on the road and figure out the best possible way for, say, the timing of the traffic lights to go on or off to make sure traffic's flowing, the best way to build an intersection so that there's the least number of conflicts possible to avoid accidents. All this stuff that needs to be done before you even start. Design, kind of the same thing. How are you going to do this? How is this going to interact with anything that's already there? If you want to build, say, a monorail type of system, you want to build it so that it's not interfering with traffic. Maybe you lift it up above traffic, maybe you go underground. You want to try and save money and do this as cheaply as possible to get the job done. Lastly, we have operation of the existing system. Kind of goes back to what I said in planning. Any type of computer program that you have, running this software, trying to figure out the best possible way, tying all of the lights in a city together so that you can start at one end, hit every green light, and make it all the way through the city without getting stuck. Any of these things that could possibly help with the existing system. Planning studies. Sounds fun, I know. Location of new highway, bridges, facility, basically anything. Where are you going to put it? What's wrong with where you're going to put it? What do you have to do? Do you have to cut through a mountain? I think we're all pretty familiar with that. Drive down 119, see where they've actually sliced through the mountain. But that's a lot of work, and that's a lot of money. So we want to avoid that if we can, or at least make sure that the mountains we're cutting through are small enough to not be as expensive as they could be. The best route that we can possibly take. Strategies for congestion mitigation in urban areas. What do we do about all this traffic? New York City, whenever there's all these people on the road, how can we possibly get them where they need to be without making a problem somewhere else? What do we do to disperse the traffic to keep it from piling up somewhere? Long-term plans. Like we said, things change over time. 15, 20, 30 years, we've all seen it, saw some pictures. It gets nasty, there's more people and there's always more traffic. And you always have to plan around this and look ahead to the future. U.S. highway system. Interstate system, if you will. Now, funny thing about interstates, if you get bored and you're a nerd, or there's something wrong with you, like myself, you'll go online, you'll type in interstate, and it'll say something to the effect of connecting 2 or more states, which is okay, until you go to Alaska and Hawaii and realize that there's not a road going to Hawaii from California, because that would be a really big bridge or a huge underground tunnel, but we still have interstates. Never figured that one out, but that's okay. So the interstate system probably been around longer than any other major mode of transportation that we have. And you can see that really, anywhere you want to go, you can at least get close with the interstate. Now, obviously, as we all know, you'll have to jump onto smaller roads, but that's not the point. Over a large area, it gives us a good way to get from point A to point B, approximately. Higher speed limits than all the other roads, no problems involved, but it's all cars. High-speed rail. The Japanese love it. We've not embraced it. And this is probably part of the reason. Japan's a lot smaller. For them to have a high-speed rail system, it's cheap, at least in comparison. This is just a proposal, but you'll notice that all of this is just left blank. It was covered by the interstate system, a little sparsely, but that's okay. But we don't even have a connection between California and New York. And really, that would make the most sense. That's 2 of our biggest population densities. But as it stands, it'd be nice if we had speed time. If it's much faster than what you normally get on an interstate. Collisions are non-existent because everything's controlled together. You don't have to worry about individuals making dumb mistakes, causing wrecks, accidents, anything like that. So it's a good idea, but it's expensive. And even the plans for it don't cover the entire U.S. Congestion mitigation. Always a problem. Especially traffic jams. Nobody likes a traffic jam. Something that's almost unique to traveling by car or truck or bus. Like we said, monorails, high-speed rails, these things don't get congested, but whenever you let individuals make the decisions and give them the chance to travel by themselves, they take up a lot of room, they take up a lot of space, and they can't travel as fast without causing accidents. So we end up with congestion, where not everyone's working together, and everyone's kind of looking out for themselves. This is what we have. And this is still a problem in all of our major cities. It's becoming a problem in smaller cities as there's more and more people, and the old infrastructure just can't keep up. Now, what are the effects? Well, now, as you all know, you get stuck in traffic, you're wasting time. Okay. You're also sitting there, usually with your car on, so you're wasting gas, which means you're wasting money. But if your car's on, then your engine's running, and in addition to wasting gas, you're also causing some pollution. One car, maybe not so bad, but every car that's stuck in traffic, it gets to be a lot. But we take these, and we have our environmental, our economical, and our social. As we said, air pollution from exhaust, we all know that. Noise pollution, maybe you don't think of it so much, but let's be honest, the guy who puts on a brand new muffler on anything that's just ridiculously loud, puts whistle tips on the back of his car, you want to go to your window when he drives by and throw rocks at his windshield. It's annoying, it's loud, and you hate people for it. Visual pollution of motorways. Okay, maybe you don't think of it a whole lot, but if you can't see what's going on, then you don't know what's coming towards you, which is always a dangerous proposition. A loss of land. If we try to make roads bigger, we're using up more and more space. And a road's only useful when cars are on it. So you're wasting land by adding these extra lanes that aren't always used. Economical, cost of building and maintaining roads. The more traffic you have, the faster the roads deteriorate, more expensive to repair them. Cost of petrol, or as we all say, gas, but petrol works. Also diesel, all the money you're wasting while you're sitting there. Goods delayed. Time is money, right? So anytime we have a shipment delayed, somebody's losing money. Social. danger of accidents, the more people, the congestion, you can't see what's going on, people cutting in front of each other to try and get somewhere 5 seconds faster. It's not good. Damage to foundations, normal stuff. Overcrowding on public transport. If the roads get bad enough, you hop on a bus, right? Because then you don't have to drive, and then the bus gets stuck, and you're back at square one. So with that all considered, what do you guys think is the most congested city? Think it's New York, DC, San Francisco, or Los Angeles? I always thought it was New York, never really looked into it. California does have a lot of people though. Washington, D.C. is probably the worst place you'll ever drive in your life. Personal opinion, but still. The winner is Los Angeles. A lot of people, and the roads just don't cope with it as well as they could. Average driver wasted more than 28 minutes in traffic. Now just think about that for a second. Anytime you want to drive somewhere, half hour, tack it onto your time. Every trip that you make, every two-way trip, that's an extra hour of your life gone for no good reason. And you have to deal with that. And they do it day after day after day because there's not been a good solution implemented. Congested cities in North America. LA, you can see right there at the top. Vancouver. Come on, Canada's empty. Why do they have so much traffic? But they're number 2. Honolulu, okay, where else are they going to go? It's an island. You can only have so many places you want to go. San Francisco, Seattle, Toronto, all just heavily congested areas. So many people and not enough. And it's getting worse. Houston, Seattle, Tampa, the top 3 increasing. 22%. That's ridiculous. For every 5 people, boom, another one on the road. You have to deal with that every day, and it just makes things slower. The top 3 decreasing. I don't even know where Edmonton is. No one does. The only Birmingham I know is across the ocean. Oh, Pittsburgh. Hey, look, Pittsburgh's doing good. Maybe people are leaving because the steel industry is kind of going downhill. Or maybe there's less people. Maybe they're doing a better job. Most congested highway intersections. So if you can see the dot really, really well, that's ridiculous. Imagine spending 69 hours every week sitting in traffic. That sounds horrible. Obviously no problems in West Virginia. At least nothing that compares to anywhere else here. But you see here in the Northeast, near DC, California, man, we talked about California. That is just a humongous zit all over the U.S. It's ridiculous. New York has a couple of areas that get congested, but LA, man, it's ridiculous. So obviously there's a problem, and we need to find a good solution to it. Alright, just a quick simulation of a ridiculous intersection, one beyond the caliber that I've ever had the joy of riding. And you see the traffic here on the interstate is doing really well. Everybody's going fast, there's no problem. But the problem you have is here at the stoplights. Maybe you can't see the cars very well, but whenever you have something that's introducing a stop and everyone has to pause for it, then there's always congestion. And whenever you have an interstate that's this busy and bringing all these people out, if you make everybody stop here, everyone just cramps together. And then the light turns green and they stay so close together to get through the green light that they just stay congested the whole way through. And it takes a while for them to break up. But you can see how well this entire intersection works. Because even where there is congestion, it gets relieved pretty quickly. So not a bad design, but it could probably still be improved. Helsinki. Transportation system. And all this is a nice quick video to give you an idea of how to visualize some of the transportation. You'll notice all the different routes of traffic and see a little bit how they interact with each other. Marvelously exciting, I know. course, you'll notice that this isn't necessarily the heaviest congested time of the day, but you will notice the brighter points are actually where traffic's starting. And you can see by the trail that they leave how much congestion is actually left there. So if they stop and it gets a little brighter, that's okay. But you'll notice as they keep moving, the trail disappears because there's no longer congestion behind them. Also notice there's different colors. Up here you have a blue line. That is the train, if I'm not mistaken, that goes through town on a set track. So it doesn't really interfere with traffic at all. You also notice it's getting across the map much faster than any of these other lines. Ah, that's beautiful. All the traffic flowing. Just a nice little simulation of what this stuff looks like in a way that you can really kind of appreciate instead of just looking at a bunch of figures and listening to me talk. Alright, so let's move on. Traffic, operation, and control. How do you control traffic? Which is kind of a weird thing to think about, right? You have stop signs, traffic lights, yield signs, all this stuff. But at the end of the day, people aren't really good at following directions. There's a stop sign. You know what? I can make it through that. I don't see anybody coming. Gone. Oh, it's a yellow light. Better press down the gas. We got to get through this one. I'm in a hurry. Oh, it turned. Yeah, you know what? Whatever. There's not a cop sitting there. We're okay. Speed limit? Come on. Nobody follows those. Oh, it says 70. Better just go ahead and go 85. We'll get there faster. There's an inherent problem with just trusting signs, but we'll try. Super corridor, future bus car. Honestly, this is the scariest thing I've ever seen in my life, because if you're driving down the road and this thing comes over top of you, you're going to panic. That's my personal thought, but if we could use it in larger cities where it's not traveling so fast and it's still able to get through all the areas it needs to, it can carry a whole lot more people than a regular car. And it's not going to hurt any of the traffic that's already traveling because, as you can see, it just goes over top. It's a pretty novel solution. Transportation up here, the super corridor, which is nice for the whole of North America. It doesn't do a whole lot for smaller cities or small towns even, but it's a really quick way to get from Canada to Mexico, if you're into that. So, roadway design considerations. Another thing to think about, right? Probably notice if you're on the interstate, there aren't really any sharp turns. There's no hairpin turns on the interstate. It's just not there. So, you'll also notice that there's no really steep hills that if you go too fast, you're going to jump them. Because if you're on the interstate, that's kind of dangerous, especially if a minivan jumps over a Geo Metro and, well, maybe they don't make it all the way over. It'd be cool to see, but not really good. And then it congests traffic, which would make things even worse. But we're going to look at ways that we can help solve that. How we handle how steep a hill is, what kind of hills we go over, and make sure that you're actually able to see something over the top of the hill, at least to some extent. So what influences highway design? Well, functional classification. You're not going to run an interstate through Boone County. I'm pretty sure there's not one through Preston County. Actually, there isn't. And there's probably a reason for that. We don't see a whole lot of traffic in these areas, so it would be weird to have 8 lanes of traffic just cut through the mountainside so we could let 20 people pass every hour. It's a bit extreme. So we have to make sure that bigger roads, smaller roads, based on what we need, and how fast you can travel based on the size and structure of the road. Level of service, same thing. How many people are going to be using this? How often are they going to be using this? Available funds, which is really the big one. You only have so much money to work with. And while it would be really cool to build that bridge to Honolulu so it would be a proper interstate, we probably can't afford to do that. Safety. So probably the reason you can't get on a little one-lane road and go 112 miles per hour, you're probably going to kill someone or land into a house. Have to keep it in mind. Social and environmental factors. Usually you can't run an interstate through a protected wildlife preserve. Just saying. You don't want to put this stuff where it's going to cause unnecessary harm to the environment beyond what any other road does. And you don't want to run an interstate through an apartment complex because, well, someone's eventually going to hit the apartment complex and it's going to be loud. Topography, the shape of the land, how you have to go around it. Design speed, already touched on it. You got to make sure that the speed you're going is not too fast, but you also don't want it to be too slow or you're kind of wasting the road. Volume, traffic mix. Traffic mix just being all the different types of traffic you can expect on the road. Alright, layout of roadways. Just an example here, you can see one lane over here, small little, just a green area, really help catch rainwater but also to separate traffic. Be a place you can put a guardrail in case you were worried about accidents. You'll notice a ditch on either side here so that water can drain off of the road and into the ditch so you don't have a whole lot of water when you're trying to drive. So we have the alignment of the road, the grade, the cross section, just to make the road. Alright, geometric design, this is where it gets fun. So highways are 3D. Your left, right, up or down, all of these change based on the road and where you are. So rather than working a 3D problem, which is kind of complicated, we break it down into two 2D problems. This way we can say, alright, this is just a horizontal plane, how sharp do we want our curves to be? That's one way of looking at it. Or you can say this is a vertical plane, how steep do we want our hills to be? How much of a crest do we want to give to that hill? How much length do we want to spread this change of height over? Things like that. Alright, and there's just a fun view of horizontal. How you're going along the road, left and right. Vertical, how do you change against a completely flat line? How much of a hill do you have? Vertical alignment, this is where it gets fun because we get to use math. Alright, proper elevation, we have to ensure drainage. Can't have standing water on a road or you'll hydroplane. I promise you it's not fun because you try to steer and you can't. The car goes where it wants to go. Not the greatest thing to do, but it happens. Acceptable level of safety. That depends on what you're doing, where you are, and what you're working with. It changes a little, but we still have to be safe. So what's our challenge? Transition between two grades. All that means is going up a hill, going down a hill. Of course you have that crest there. You have to be able to come up the hill and see if something's coming head on over the hill. Or if there's something in the middle of the road, something you can avoid before you hit it. Generally the way to go. Two things we have a crest, which I've been talking about a lot, and we also have a sag here. Not talked about a whole lot, but still a problem. Especially if it's an extreme sag and you come down it fast and you drop your back end into the road and just scrape your bumper off. Lose a couple of car parts, not fun. Alright, so we're going to base this off of the stopping sight distance. How far ahead something is that you can see it and be able to stop. We need a length that will provide a sight distance S, which we're going to get into. And you have two different situations, and you're looking at a 3.5 foot driver eye height. So you're sitting in your car, driving along, your face is probably about 3.5 feet high, maybe higher, maybe you're driving a Hummer or something, you're 6 feet up and you can see everything in the world and run over people you don't like. 2 foot object, things that are 2 foot tall, small children, not fun to hit, their mothers get mad, dogs, owners get mad, center blocks, you're probably not going to drive anywhere else. If a tree falls 2 foot high, that sounds pretty reasonable. Things you want to probably try to avoid if they're on the road, 2 foot height, pretty good. Alright, so we're going to jump into some formulas, which I know everybody's looking forward to. Just a couple of symbols. PVC, beginning point of the curve, right here. PVI, point of vertical intersection. If we take the slope from one gradient and the slope of the other gradient, PVI is the point at which they meet. Alright? PVT, point of vertical tangent, the end point of the curve, which is where we end. It is this point right here, which is where we get this line from. Okay, now the initial and final grades are G1 and G2. Write this down. I can go back to the slide if necessary, just to make sure you guys are actually able to keep up with what we're about to do. Excuse me. Alright, fundamentals. This look fun to everybody? It looks fun to me. So the length that we have here to work with between our starting point and our ending point, shown down here is L. Halfway point is L over 2. Simple enough. Why is L over 2 important? Because that's where our PVI is going to be. G1 being the grade of the first slope, being percentage usually. Same thing with G2. This right here, if you're not familiar with it, it's delta, which is going to give us our difference between G1 and G2. And X here is just the position that we traveled purely horizontally from PVC. So we're not talking about the distance that's covered on the road. We're just saying, okay, it's here. Our X distance is right here. Alright. If you weren't having fun before, I know you're having fun now. General mathematical formula for vertical curves. This is something I would probably write down. That's just me though. So y is equal to ax squared plus bx plus c. You guys have all had enough math to do this, so you should know exactly how this works. The easy part about it, we're going to give you a. G2 minus G1 over 2L. Gave you G2, that's the grade of the second slope, right here. Gave you G1, grade of the first slope, right there. 2L, what's 2L? Well, we just take L and double it. Simple. What's B? B's even easier. It's just equal to the grade of 1. Y is just equal to C. Simple. Now, important thing to note, G1, G2, in decimal form, L in feet. If G1's a decimal form, G2 has to be in decimal form. We can also do G1 and G2 in percent and L in feet. Same thing applies. Don't mix decimals and percent. Bad news bears, don't go there. Here's where you guys come in. Fun example. A 400-foot equal tangent crest vertical curve. Man, that's a mouthful. Isn't that awesome? Alright, it has a PVC station of 100 at 59-foot elevation. The initial grade is 2%, and the final grade is negative 4.5%. You guys don't let that mess up. A negative grade just means that it's going down. Positive grade just means that it's going up. That's all that is. Alright, determine the elevation and stationing of PVI, our center point right here, and PVT the curve. Also determine the curve elevation at x is equal to 1.23. Alright, so you guys come into groups at your tables, start working on this. I'll go back to a slide if you need me to. If you need help, I'll walk around and we'll see what happens. Alright. A couple of you came pretty close, a couple of you got it. It's all good. So we're going to go through this together and look at it. So we have a 400-foot vertical curve. So the elevation of our PVI is the 59 foot, which we were given. 59 feet actually. I should learn how to talk. Plus 0.02, why 0.02? That's the 2% grade that it gave us in the problem. And 200 feet. Gives us 63 feet. Pretty good. Elevation of the PVT. We take the 63 feet from the PVI, which is our highest point, and then we subtract 0.045 because 4.5% and 200 feet. Gives us 64 feet. Everybody good with that? Awesome. So at x equals 0, y is equal to c. C is just equal to 59 feet. Same thing we said in the problem statement. Information given. So here, from our formula for the curve, we know that A is equal to G2 minus G1 over 2L. All we have to do is plug that in. We get A, negative 0.8125. Pretty good, nice and simple. So the curve equation that we get, minus 0.8125, x squared, that's supposed to be squared, I promise, plus 2x plus 59, all this from the previous slides, and the elevation at x is equal to 1.23, all you have to do is plug that in at x, and you'll get a y is equal to 60.23 feet, where x is 1.23 feet. So if we start here and we travel 1.23 feet, we are 60.23 feet high. Whew. Man, that was fun. Alright. Now, going back to being able to see over the crest. These guys were doing it the easy way, no math involved. You go out with a sighting rod, say, hey man, go over there as far as you can, I can still see you. We're going to sight this, see what the length is, and get it down. And that's still a 2-foot high object, observer, 3.5 feet. Pretty reasonable. Horizontal alignments. Whew. All sorts of fun. What do we have to worry about? Transition between two directions? Okay. Going left and going right. We've all been there, done that. Horizontal curve, same thing. You want to be comfortable. It sucks going around a curve that's just too tight. Your vehicle has a little roll, so you're still steering left, and your body's over here. You have to slow down or something. It's not fun. And this is what you're dealing with. You're on an elevated plane on one side, a little lower on the other side, which causes this extra force down here. Of course, you'll notice FCP is greater than FC. So FC being the force of the car whenever you're in the turn, FCP, what we get is the force you're going to experience because you're on this slope. So something you have to keep in mind whenever you're designing these, so that whenever you're going across them, it's not too much force, or even worse, if you're going across it and it's too steep and people start to slide down the slope. Good coordination of horizontal and vertical alignment. So if you do it right, it looks beautiful. Well, I think it looks beautiful. You might disagree. You might say it's just a road. But it looks beautiful. Just trust me. Doesn't affect scenic, historic, cultural resources along the way. So you get this beautiful view of mountains on the side and across from you. Sometimes we cut through them, but it's still beautiful. If we do it right, it enhances the attractive scenic views. You'll be able to actually look out your window and see the rivers, see the mountains, see the skyline, everything that's going on around you. And hopefully all the deer that are scampering about beside the road. Outstanding buildings. So the idea is if you do it right, you're still able to see everything around you without the road itself getting in the way, which is really what we're aiming for. So now that we've talked about how to design the road for the car, let's talk about stopping a car. Okay, buddy, we know how to stop a car. You press the brake, it slows down, you stop. And you're right. And sometimes there's problems. As it is now, there's a lot of ice and snow on the road and makes it a little more difficult. It might take a little longer. You might just go sideways and go in a ditch, and you still stop because you're in a ditch. But we're going to talk about thinking distance. And it's something no one thinks about, which is weird given the name, I know. But that's okay. Thinking distance. You have to realize there's a reason to stop before you stop. If your eyes are closed and you're driving, which I don't recommend, you'll probably get pulled over. I'm not speaking from experience, of course, but it may happen. You'll notice that you don't know when to stop unless you start hearing people scream, because you can't see anything in front of you. That's a given. So whenever you can see things in front of you, you have to react to them. And no one reacts immediately. There's always a pause. Maybe you're distracted, or maybe it takes a while for it to be in your field of view. But regardless of what happens, there's a distraction that you have to overcome. So once you realize it, the amount of time it takes you to realize it, and then the amount of time it takes you to do something about it, that's what we're talking about with thinking time. And stopping distance. Okay, you're going to tell me the exact same thing. Yeah, we know stopping distance. You hit the brake, stop, whatever, it takes so long. And you're right, and that's fine. But we have to consider these two together. Stopping distance, exactly what you said. How long it takes you to stop the car. And it depends on a couple things, but we can usually figure it out with a decent accuracy. Thinking distance. Too much alcohol. Generally speaking, if you're drunk, your reaction time's awful. If you can even stumble into a car, which is why there's a law against it. Tiredness. If you're really sleeping, just nodding off and can't stay. Oh crap! Stoplight. Whew. even an officer, it's not good. And it's going to take you that much longer to see something coming. It's almost like driving with your eyes closed. Too many drugs? Okay, and just to be fair, if you've had too much heroin or cocaine, you probably shouldn't be driving. But that's not where we're going with this. Maybe you took NyQuil because you're dumb and decided to take a long drive. Or maybe Claritin, anything that makes you drowsy or messes with you. Maybe something you ate or something you took is making your face swell up a little bit. Anything that's going to just agitate you or make you a little slower. Poor visibility. As far as I'm concerned, there's two options you have here. Either A, you can't see, and you should be wearing glasses. Also in that same thought, if you're one of these guys who has their windows tinted so dark that light cannot go through it, and you turned your window into a wall, also poor visibility. Or maybe it's just awful outside. Maybe it's foggy. Maybe it's heavy snow or heavy rain and you can't see more than 5 feet in front of you. Stopping distance. Wet roads, wet icy roads, snowy roads, gravel on the road, dirt on the road. All of these things make it harder to stop. Oh man, I hit it twice. What a bummer. So, driving too fast. Hey, if you drive faster, it takes longer to stop. Duh, right? So, maybe don't go 80 whenever the speed limit's 25. You may not be able to make the stop before you hit the stop sign. Alright, tires, brakes worn out. Okay, if your tires are bald, it's going to take you a while to stop. If you don't have brakes and you're, hitting the brake and you're just tearing up your rotor, it's going to take a while to stop. If your brakes are garbage, it's going to take a while to stop. Alright, icy roads just like wet roads, only worse. Alright, I want everyone to watch this very carefully. This is probably the most important thing you will see for the rest of your adult lives. It's a beautiful example of thinking distance and stopping distance. Reaction distance, how long it takes to recognize there's something in front of you. Amazing, isn't it? Ready for another one? Anybody know what that is? Yeah, I know, I'm being dumb. Of course it's your braking distance. You have to have one before you have the other. And if you add them together, what do you have? Yeah, your total stopping distance. Of course, as you'll notice here, this is 10 inches and this is 10 inches and this is a really, really long 10 inches. So we'll have to work on how we actually add and make sure we don't mess up. But nonetheless. Alright, you guys ready for more fun? I know I am. Everyone is. So, just a match game. Hopefully I've got some stuff to give out. Usually frisbees. I like frisbees. Teachers hate them. Alright, so stopping distance. Anybody know what stopping distance is? If you said the sum of thinking distance and the braking distance, you will be correct. Alright, anybody? Friction. Friction, friction, friction. Nobody? Dang. So, if you said friction and you thought maybe one of the forces the road exerts on the tires as the car is stopping, you will probably be right. Alright, thinking distance. Alright, we've only got two left. The distance a car travels, or the distance a car travels. Oh wait, those are the same crap. Thinking distance probably has to do with thinking. Happens before you do anything. Before the brakes are applied. I'll go with that. Man, we're doing good. So, braking distance, by process of elimination, must be the distance the car travels whilst it is braking. Good job. Alright, get to have a little more fun. So, stopping distance. Keep talking about it. Maybe it would help if we had a way to solve for this mystical thing called stopping distance. Oh hey, we did. Isn't that clever? Man. So, you take this filled with all these symbols and a couple of numbers, which is basically all engineering is symbols and numbers. That's not true. There's fun stuff too. But this is a good part of it. And we do this for you so that you don't drive yourself absolutely crazy. Oh, SR, okay. Reaction distance, gave that to you. 1.47, it's just a constant, don't worry about it. It's going to depend on different things, who the person is, what kind of visibility they have. But here we're just going to say it's a constant. You have SI here, final speed, miles per hour. Units very important, as we all know. T sub R, reaction time in seconds. Also good. Braking distance, SR. Must be braking distance. SI squared minus SL squared. We go down here. SI, initial speed. SL, final speed. Beautiful. All over 30 times the quantity of F plus or minus 001 G. G being our grade. F, of course, being our friction factor. And let's put this to some use. Alright. Highway, safety, and driving. Okay. We've covered a lot of that. We'll cover a little bit more. It's all good. So, distraction, driver-related decisions, looking at things outside the vehicle, looking at things inside the vehicle. I mean, we see this guy, girl, one or the other, I can't tell, but he has 2 kids in the back, and they're getting along, which if you've ever been in the back of a car with a sibling, you know that's not how that works. You're going to be fighting probably for the 6 hours it takes you to get to the beach, or maybe that's just my family, I don't know. And your parents are going to be looking back and yelling at you and telling you to quit it and get on your side. You get on your side. Stop touching him. And it's distracting. Wireless devices. Okay, if you're on your phone, I want to slap you whenever you're in a car because you're not paying attention to what you're doing. There's more on that later. Experience. If you know what you're doing or not. Especially in road conditions we've been having. People in the snow. Oh, I'll just drive my 2-wheel drive 200-pound car up this really steep icy cliff, and I'm stuck. Okay, a little bit different here, but depending on how well you know how to drive is how you react in a situation. Maybe you see something coming towards you and all you do is hit the brake and it still hits you. Whereas if you have a little more experience, you might try to swerve out of the way. Vehicle-related brake issues, tire issues, motor issues, anything wrong with your car. Roadway condition, design, traffic volume, pretty self-explanatory. Environmental, weather, lovely weather. Human factors. Alright, perception, reaction. Basically, perception, talk about what you can see, what you can observe going on around you. Reaction, how quickly you do react to it. Driver's abilities and limitations usually goes back to how well you can see, how well you can react. What you know how to do whenever you're faced in a bad situation. Cognitive processing, how quickly can you think about it? And even more importantly, how well do you think about it? I see a tree falling, I'm going to run into the, no, don't run into the tree. Hit the brakes, okay, I'll stop before I hit the tree. Or maybe it's really close and you need to speed up. How quickly you can process this and figure out what you need to do. Alright, so visual distractions. Eyes on the road. Simple. Cognitive. Mind on driving. Manual. Hands on wheel. If your hands aren't on the wheel, it's harder to steer. You can use your knee, but it doesn't work very well. If you've ever tried. Alright, anybody know the major source of driver distraction? How about if I give you a couple options? Alright, sleepy, tired, reading, writing, eating, talking on a phone. Anybody have a guess as to which one is the biggest cause of distraction? Because if you said talking on a phone, you would be correct. And man, it's annoying. Alright. At least 1.6 million crashes each year involve drivers using cell phones and texting. Especially with a touchpad phone, you can't text when you're driving, because you have to look at the phone to see what you're doing. Even if you're just talking on the phone to someone else, you're not paying attention to the road, you're paying attention to the phone. So, luckily, in West Virginia, we have a handheld ban for all drivers. And a ban on texting for all drivers. Of course, they still do it. But as more people get caught, more and more people have to pay the fine. That's going to decrease. It's going to help us improve the safety of the roads and overall help us how the roads operate. Hopefully. Hopefully. All right. And with that, we're going to end this presentation. Hope everybody had a fun time. At least I had a fun time, and that's all that matters to me. So if you have any questions, I'll take any questions, comments, concerns, anything that I left out that you want me to cover, we can go back to.